Hi, Nino. You are now the host.
Hi. So we'll start in 3 minutes, correct? Yeah, good. Thank you. Yeah, so what I will do to actually kick off this meeting in 2 minutes is I will go through the presentations, and there are several questions, and I will pick one from each session, and so we kick off, and then we go a second round to pick up other questions. So thank you very much, first of all, for all of you to come. It's really a pleasure to see you all. If we cannot meet in person, unfortunately.
No, do you see anybody from the attendee list who needs to be promoted to the panelist?
No, not
okay.
at this
you are the
moment.
Yeah, you only promote the
Yes.
speakers to the panelists.
Yes,
you are now the host.
yes.
Only you can promote.
Okay, thank you. But no, I don't think.
Okay.
Well, give me one moment.
Okay, pause chat.
Okay, I think we are ready to start our panel session and question and answer meeting. First of all, thank you all to come to this live session. And as I said a moment ago, it is a pleasure to see all your faces. Good afternoon, good night, good morning. So we are spread really around the world. We have people from China, Japan, New Zealand, US, Europe, and it's really a large audience. And thank you all. Especially the Europeans at this moment, it's very late in the night, so this is a good time to actually discuss interesting topics as wireless power transmission. And I think we are all here because we are passionate about this topic. First of all, let me say that all the videos are having a significant number of views in our platform, so this is very good. So we are attracting a lot of interest, and we have videos with 500 views and videos with 100 views. So in average, I will say it's higher than 100. So this is very good for promoting this school. So as you know, the Wireless Power School is actually sponsored by the IEEE WPT community. So you are all invited to join us at wpt.ieee.org and get a lot more information from wireless power and contribute also to our activities if you are interested on this topic. So the way we are going to actually kick off this discussion, I will go through some of the questions that you have been adding to our WUVA website so that we can actually kick off some of the discussions. And if you have extra questions, or if you want to put questions live, please use the question and answer button that you have in your Zoom platform and write your questions there. I will make it available for all the panelists here today. So having said this, I will start with the first question, which I have here. So this first question is from our first speaker, Gran Kovic, and the question that I have here is how much, and I pick one of the questions that you partially answered already online, but how much efficiency multi-coiled IPT inductive power transmission, exactly same MIMO based systems for IPT. So how much efficiency do you think the multi-coil can actually achieve in these new systems?
Okay, so that's has so many answers depending upon the use case. But what I'm going to try and say here is that multi-coils obviously find their place when you have a lot more tolerance or a lot more power, and you're thinking about transferring power and constraining your leakage, so that as a primary, you can shape the field to try and get a better coupling to your secondary if it's misaligned. And that immediately, if you can get an effective coupling which is higher by shifting the phase of various coils relative to each other, you can enhance the power transfer. From the secondary side, you can have a secondary which may be moved relative to the primary. And the nature of, and so multi-coils there are really helpful. So for example, an easy one to understand is if we put a circular coil as a secondary, then it's really going to be responsive to fields which come vertically from the primary. But if it shifts lateral, what's happening is that at the center of that pad, you're starting to see the more horizontal field, because the fields come out of a primary circular like this. And so they become horizontal. And if you move that secondary, you can see in the horizontal part of the field, and the circular won't pick it up. But if you put a double D on there, which is responsible for a horizontal field, then it will pick up that field. So what's happening is field is a vector. It has horizontal and vertical components. And if you have two coils in that pad, which are individually looking at the vertical and horizontal components, you can extract the field out of that's already present and extract power effectively. And if one of those coils is not producing power because it's perfectly aligned for a horizontal field or perfectly aligned for a vertical field, you can shut that coil down. So you can get really good efficiency gains because you're maximizing the coupling and you're reducing the loss of that coil on the secondary. And I think that's it can be a much more complex answer, but I think that's probably enough for the moment.
Okay, thank you very much. And I have a question also for Dolipa, which was also one of the speakers of the first talk. From the questions I saw, there are several questions asking what is the best simulator that we can use to actually simulate some of these structures, mainly for low frequency inductive coils. So I saw in the questions talking about HFSS, CST. What is your opinion? Do you have an opinion about this?
So it depends on what you're simulating and what's your end goal. We use a combination of a number of different simulation tools to simulate ad hoc. So if you're looking at the magnetics, then a good starting point would be using ANSYS Maxwell or something similar like COMSOL for low frequency applications. And then that would give you your expected coupling coefficients, your inductances, changes in inductances, and so on. Then usually we take this information and either use, if it's a simple system, we end up using LC Spice, but for more complicated systems, especially when we want to simulate also system level, we take this information into Plex. That's So we use the Plex toolbox or the block set that integrates with MATLAB. So we can also use MATLAB Simulink features together with Plex to do sort of more system level analysis and simulations. And after you got that information onto Plex and MATLAB, then it's sort of, we have scripts that we write to analyze it under different conditions, sweep it across different sets of variables. Then we can get a good understanding to how these systems behave electrically. Now, if you want to add more layers into it, for example, look at core losses or look at switching losses, then we keep adding those complexities after we get the basic sort of electrical specifications met. So that's how we build up the simulation models. It does take, and also sometimes we had to go back and look at on the bench and see whether these models do make sense. So once we've done the ANSYS simulations, we would go and measure the coupling factors in the lab and the inductances in the lab. And sometimes Grant can probably add, we use a jig which takes the pad up and down, and then the LCM is programmed so that it measures and spits out all the coupling factors at different XY coordinates, XYZ coordinates. So this, and then this information together with the simulation models get fed into the electrical model. So it depends on how accurate the simulation model needs to be and how detailed you need to capture things.
Yeah, and a lot of these things we're also interested in maybe getting a little bit more into details after we've done that basics. We might want to look at where there are particular losses in the system. So we want to look at voltage and current stresses in both the electronics and the magnetics. We want to look at the thermal stresses that might be in the ferrites, or even the collective stresses that happen when you encapsulate a pad and you lay out things. So sometimes that can be quite complex. It's quicker to actually test it in the laboratory. But at times, I mean, the modeling in ANSYS enables, and COMSOL enables you to do the thermal analyses, to do eddy current losses, and as well as all the leakage factors. So these seem to be the next layer that you go to once you've got a basic design you're starting to be happy with.
Yeah, thank you very much. But do you think, and before I move to the next talk, do you think actually the models are good enough? So how far are the simulations from the real thing?
It depends on how much effort we put into tune them. So it's not like you have the model and it goes and you get exact same results on the bench. We have a closed loop system. So we sort of, for example, if it's switching losses, we predict the initial ones based on the data sheet, and then we go to the bench and measure them and fine tune the models. So it depends on how much fine tuning you do. Same with the thermal models, you go and measure things in the lab, characterize the thermal properties of the materials we use, then you put that into the simulation model. So we had to verify each stage and calibrate each stage. Then you get a really nice sort of, towards the end, it's a nice matching model. But that takes maybe an year, maybe more than that. Like Grant can probably say, Seiho probably spent 3 years calibrating his models. So
yeah, I'd say it depends on what level you need. So if you can take nice lumped models, and they get you within 5%, maybe worst case 10% if you're being really rough in your lumped model for magnetics. But then if you want to get down to all of some of the really nitty-gritty thermal issues, you might go down to the wire level in your modeling. But you generally don't have to do that for the more general modeling. If you want to stay within around 5%, that's not too bad. It's when you want to predict some of the more difficult behaviors, that's when your model starts to get a little bit more refined. But most of these packages are pretty good as a starting point, using lumped analysis and sort of getting, because you're often looking at the more trends. I mean, if you think about it, you're not looking at working at one particular coupling factor. You're looking over a range of coupling factors, over a range of inductance variations, and so you're looking at the stresses at each end of the system and the variations you have. So you want to do that in the quickest way possible to see if you're in the right ballpark, and then you might refine it.
Yeah. So like Grant was saying, the starting point would be we simulate the coils using basically a lumped copper sort of a that looks like the shape of the winding, but it's a copper sheet, and the ferrite is just a ferrite base, not the individual blocks. But then you can keep refining. And to give a rough idea, if we had the right data sets from the manufacturers for the ferrites, then we could get all the way up to the losses predicted in ANSYS to about 10 or 15% accuracy. And then it's a matter of refining. And so if you want to refine it, then we would take the ferrites, take it to the lab, characterize the loss curves, put it ourselves rather than relying on the manufacturer data sets. So then you get a bit more accuracy out of that.
Okay, thank you very much. I think it was clear, and it's nice to see that this is an iterative process. So moving now to the second talk that we have in the platform, and this question is to Paul. So one of the questions that I think got more votes here in the question and answer is, which topology of inverter is best for megahertz range of WPT? So do you have any opinion on that?
So hi everybody. Apologies, I'm pretty tired at the moment. I've been driving 6 hours today, and so if I sound a bit croaky and not quite up to form, excuse me. Yeah, so the inverter question got some interest, didn't it? So one of the things that we try and avoid when we're working at megahertz is to use any sort of class D type switching. So if you go back to the way that you define the generation of different voltages within any form of inverter circuit, the sort of very typical thing that most power electronics people will be very familiar with is the class D type of operation, where typically you have a half bridge that you may put together, multiple or two half bridges to make an H bridge, to make a full bridge. And that bridge is fed off a DC bus. And so the output of the bridge generates square wave voltages. And the difficulty with operating that at very high frequency, once you get into the megahertz, if you think, the sort of rise and fall times that you need operating with a 100 kilohertz fundamental, you need to be 10 or 100 times faster than that when you start going into 6, 10 megahertz, etc. And so creating class D type square wave voltages in the ISM bands is pretty difficult. Consequently, we tend to move instead to class E type solutions or derivatives of class E. So if you think, what you're effectively doing is you're putting in a resonant network around the switch in order to control the trajectory of the drain source voltage across the switch. So you're avoiding that step change in voltage, creating a square wave at the output of a half bridge where you've got perhaps some ringing that is difficult to control. You're intentionally putting in a resonant network to control the shape of that voltage. And so then you get this class E type of waveform, or indeed, we tend to use a derivative of that, something called the class EF. And we have a particular design of class EF, which is load independent. So one of the things with all of these topologies, when you look at any form of inductive wireless power transfer, or indeed capacitive, is operating the inverters and the rectifiers at the right operating point, so that typically you try and operate with very low switching loss at these frequencies, so zero voltage or zero current switching. And it's tricky to get that to operate over a very large load range. So if you change the distance between the transmitter and receiver, or you just change the reflected load because you're charging a battery and it's getting charged and the charge rate is starting to decrease, you've got to be careful in all of this as to designing something where you can maintain the zero voltage or current switching over that large load envelope. And this class EF design that we use can operate typically from a short circuited reflected load all the way up to 10 or 15 ohms, depending on how you design it. And that's typically what we use there for. So it's also single transistor low side switch, so you don't have to worry about high side gate driving. There's lots of practical reasons why we find it works pretty well at megahertz. We have tried class D type solutions, half bridge solutions. We have got them to operate, but we found the ringing to be pretty difficult to control when producing the square wave voltages.
Thank you very much. And I will include here also a question that came via the Zoom platform, which the question is, with WPT, does power increase linearly or quadratically with an increase of operation frequency? And also what assumptions are being made for that? Do you have and this, of course, to you and also to the previous speakers.
Yeah, so if you increase the frequency, then you increase the, if you double the frequency, you double the rate of change of flux. So you double the received voltage, so you would get 4 times the power for the same reflected load. But of course, it's not as simple as the basic laws of physics here, because other things are at play. And I think one of the very important things that's at play here are the regulatory aspects, which I'm sure that Mauro will be able to talk about in a bit more detail later. But if you look at, for instance, the ICNR IRP limits, the magnetic field strength you can create rolls off proportional to 1 over frequency, at which point I think the power you can transfer up to the limit is the same independent of frequency if you're on one of those parts of the slope.
So I would like to add that, in fact, I could also argue at high power, it doesn't do it at all. So one of the challenges you've got is that you hit a voltage limit. So you've got all sorts of voltage limits with your electronics, with your magnetics. You don't want to have corona effects. So once you start hitting those voltage limits, in fact, you've got to constrain your voltage. And once you have to constrain your voltage, actually increasing the frequency doesn't necessarily, apart from lowering potentially the leakages and that sort of thing, doesn't really help you that much. The current tends to be more the part that you're playing with to work on increasing the power. So it becomes a real, in the low power range, you can certainly increase your frequency and increase your power, but as you get to the high power range, there's a whole pile of other things that start to bite you here, and so then you start having to work through the practical issues of wireless power transfer and what you have to do.
So it's probably just worth saying there, while I've still got a little bit of voice left, that sort of highlights that typically the work that we do at Imperial tops out at sort of 2 or 3 kilowatts, whereas Grant's probably just getting started at that sort of power level. So.
Okay, thank you very much, and I will move now to the third speaker, which is Karam. I saw several questions in your talk, but I think what people want to know is what is the difference between capacitive WPT and inductive WPT? What is the main difference, and how do you think the efficiency of one versus the other will combine?
That's an excellent question, and I try and address that to some extent in my talk, but let me sort of highlight some of the major differences. So fundamentally, it is the dual of magnetic wireless power transfer in the sense that now you're transferring power through electric fields. So you're essentially leveraging higher frequency electric fields to create large displacement currents through these parallel plates essentially that you have in your system. The big difference comes from, first of all, the fact that we don't have magnetic monopoles, but we do have positive and negative charges. So the electric fields start and terminate on those plates as opposed to magnetic field lines, which will flow through the loops and return back, which is why in magnetic field systems, we either have ferrites to guide that flux, or we have coils, additional coils to essentially reroute the magnetic field lines. So that itself, that basic difference is what gives rise to some of the advantages of the electric field systems, but also create the major differences. The other big difference between electric magnetic field systems, which goes in favor of magnetic fields, is actually a major negative for electric fields, is the difference between the permittivity and the permeability of free space. So the permeability of free space is more than 5 orders of magnitude higher, which means for electric field systems to be able to compete with magnetic field systems, you have to compensate by changing the electric fields by that many orders of magnitude faster, if that's the only control handle you have, in order to essentially get the same kind of displacement currents to flow as you would induce voltage in a magnetic field system. Now, there is a subtle difference, which is that carrying hundreds of amps of currents is a lot harder than to have hundreds of volts of voltage. So there is a difference in numerics, which goes in favor of electric fields, but certainly not to compensate for the big difference in permeability and permittivity. So I would say at the heart of it, those are the scientific differences. So the fact that the permeability and permittivity are numerically very different, and the fact that you don't have magnetic monopoles, but you do have positive negative charges, gives rise to all the other differences that we find in the system. So I can elaborate on the engineering differences, but those would be the fundamental scientific differences.
Yeah, and one other question that I've been seeing when we talk about capacitive wireless power transfer is on the coverage distance, maintaining the same efficiency, let me say. How do you think you can compare the coverage of capacitive versus inductive? Are similar? Do you think the magnetic field goes down faster than the electric field? Do you have an opinion on this?
In terms of the end-to-end efficiencies that you can achieve from the two systems, you can achieve comparable efficiencies. They may not be exactly the same. It all depends down to then engineering, because you have to operate at much higher frequencies, which obviously means more losses in terms of switching losses or any other induced losses in whatever dielectric materials you may have. So that's so there is that subtle difference. But in terms of, you do have other advantages, like Paul was mentioning, that you can get higher Qs by going to higher frequency. And in capacitive systems, you're using inductors to essentially act as your compensating elements. And because you're operating at higher frequencies, those inductors can be very high Q values. So for example, our systems that we've built, we've had Q values for inductors as high as 2000. Now it's very hard to achieve those kind of Q values for the coils that you may have for a lower frequency inductive system. Plus, by the time you add in the ferrites and their losses, you have additional losses in magnetic systems. So I think end in end, overall, it's of the same order of magnitude efficiencies that you can achieve from the two systems. Comes down to the engineering.
Okay, thank you. Thank you very much for this interesting discussion and talk. So now we'll move to the fourth talk, which was on the electromagnetic compatibility of these systems. And we hear Paul talking about kilowatts. And this question goes to Mauro. So how do you think kilowatts and EMC combine together, when in principle some of these systems will have also a human involved somehow in the middle? So can you address this issue?
Yes, I am thinking about this since I'm writing the white paper of EMC for the IEEE WPT initiative. There are a big difference between low frequency and high frequency fields, because in low frequency, WPT systems are intentional source of magnetic field when we are considering inductive power transmission systems. So if you reduce the magnetic field, as in EMC design, you can have a strong reduction of the WPT performance. So you have to be very careful about reduction of magnetic field using shields, for instance, conductive shields. So you can use ferrite or other similar materials, or additional coils, reactive or active coils, to produce a magnetic field which is opposite to the incident one. But you have to stay very careful about this approach, because you can degrade the WPT performance. As regards the human exposure, obviously there is a big concern because the fields are very strong. You are speaking about kilowatt, but there are also megawatt. For instance, in Korea, there was an experiment with a train with 1 megawatt of power. So there are very high level of magnetic fields. Please also note that the international regulations for EMF safety are based on acute effect. It means short-term effects. And there is nothing about the long-term effects, for instance, cancers or leukemia or some other disease. And this could be a problem for the future, as happened in power lines. And as regards high frequency, there is a very big difference between the past because the power is higher. For instance, in the high frequency, you transmit power and signal at the same time, sometimes. But the power is much higher. And also, now there are massive antennas, and also there are some other techniques to focus the fields in some specific points, while the regulations for EMC and EMF safety are not ready to protect humans against so localized fields. And so there is a big problem, in my opinion. Thus, in conclusion, I think that the environment, the electromagnetic field safety, and the other similar aspects are very critical for the widespread use of WPT systems.
Yeah, and let me, I saw also there is another EMC question on another talk, but I think you can potentially discuss it, which is on the solar power satellite. So on solar power satellite, we are talking about huge fields, probably coming from satellite to ground. And EMC is no longer only a problem to humans, but also to the environment, probably, and to several. And one question that rise up all the time is what will happen to the birds, right? So this is really a big problem. So how do you think this can be, how can we cope with these large beams of energy in order to reduce the impact in the environment in this scenario? How do you think we can evolve in order to so that this becomes a reality, but we do not violate the EMC rules that are there at the moment?
The question is for me, Nuno?
Yes, for you.
I have not any experience about solar energy. Professor Shinohara probably is much more expert on this topic. But in the past, I worked on EMP, electromagnetic pulse. The electromagnetic pulse covered a region, a continent. And there was a big power in a few instants. And there are some techniques to increase the immunity of the electronic and electrical systems. But in any case, I don't know what's happening with solar.
Okay, thank you very much. And now I will move to the next talk, which is going to be Uman on radiative wireless power transmission for satellite applications. And one of the questions that actually I see in the platform is how solar power works in case of satellites. That is, how can we take profit out of these WPT in satellite communications or in satellite operation? Can you give some?
Sure. Yeah. Hi, everybody.
Hi.
So this is something that we've been kind of looking at as far as, I mean, one of the big issues with the solar panels is that, you know, the flux so you have a fixed flux from and in space, the solar flux is higher. And then you have these panels that, so they operate very well. So, I mean, obviously that's what they use, but the issue is deployment. So when you launch a satellite, it takes ages, you know, days and days and days to deploy it fully. And in the middle, the batteries are supposed to, I mean, the life of the sensor platforms are limited to the battery use. Now, how you could so there are some lessons to be learned from the space to ground solar SPS work that has been going on, is whether we could have something like a grid system in space where you could charge, you could have satellites that will have rectennas on them, and they don't really have solar panels on them, because the rectennas could be much more higher power density, so they could be smaller. And then you have these grid systems, these big solar panel areas, where they absorb the solar panels and then they radiate, let's say at 2.4 gigahertz or 5.8 or whatever frequency we choose, and then the rectennas power the more smaller sats. And a lot of this work is actually going on the design platforms, on CubeSat technologies and everything else, because the CubeSats, if you look at the CubeSats, it literally is just a solar panel. Everything else is already compacted. So the question would be is, how do we get rid of those solar panels? And so that's one direction for sure. The other direction would be is obviously the laser power, the wireless power with lasers, where you can now make, if you have the pointing and tracking, you can make the panels much smaller, and because now you're in a collimated beam, and you can start to use that. But the existing panels could certainly accommodate the laser, high power lasers. At the same time, I would say, you know, multi-modality panels might be a good thing to do, where you can pick up power from, I mean, actually, you know, a lot of the talk is about, you know, taking the solar flux and then radiating it back to Earth. There is something to be said about radiating back into space from the ground, because we do have a lot of energy here, and it's a lot simpler. And you could have a conduit going the other way, especially for LEO orbit. So that's, you know, there are multiple opportunities that we're kind of investigating, and it really depends on the pain factor for these satellites. A lot of them, the solar panels are to a large extent engineered correctly, the foldable ones and the multi-junction ones, and the industry is kind of moving out on them already. So to change that, it will require a serious need. And some of that is coming with, if you look at the lunar capabilities with the dark side of the moon, where there is no power there. So how do you transfer the power there? And on top of that, you know, they're having major, let's say, relay stations within the space, which I think that's going to be a great opportunity for wireless power transfer in all its modalities.
Okay, thank you very much. I think it was a very good answer, but there is another question here that I think is very interesting, at least from my point of view, which is my field of interest also, which is swiped. So simultaneously wireless and information power transmission. How do you think this can be viable from satellite to Earth, or do you think this is viable only inside the satellite? Like sensors inside a satellite or something like that. So how do you think swiped can be of interest within this WPT community?
Yeah, so actually it's kind of interesting, because this is something that I've been pushing within the company and globally to some degree, is that in this day and age, we don't really want to push power from point A to point B. What we need is, and 5G is pushing this really hard if you think about it, what we need is signal and power. So it's about you know, let's say kilobytes of data per unit joule. And satellites do this all the time. So they have a certain amount of power. The biggest issue with satellites is that the communication between the satellite and ground is limited by, to a large extent, IEEE power levels, which are very, very low. And the reason for that is because we have very, very high receivers, high quality receivers on the ground. With a wireless power, we're going to transfer a lot more energy back and forth. So space to space is definitely is a great idea, where you have, especially with these base stations that are going to be built on the way to Mars, for example, they could be the comm centers, and they will be radiating information. And information would not necessarily be data transfer, is more aligning, tracking, positioning. For example, you know, in this quadrant, you're going to see, let's say, 200 watts of power being available at this time. So then each unit will arrange itself to accommodate for that. So there is a lot of tracking information that is actually could be used for that. And we're kind of looking at that. It is intriguing. The only question is, I think a lot of people who work on the space side, they're very, very hesitant to get rid of any solar panels or any direct power on their larger satellites. So the best parts, I would say, is the microsats, and especially close to something like a, you know, International Space Station type of thing, which is, I think that's where the angle is coming from, is going to be a network of wireless power and signal between. So a satellite is no longer one unit, it's going to be like 5 or 6 units, and each unit will do a different work with her, and you have to comm between each one of them. But that's kind of, I think the future is going to dictate that to a large extent.
Okay, thank you very much. We'll proceed now to Naoki, and one of the questions, in order to connect with actually human, is really on these solar power satellites, what do you expect will be the efficiency that you are seeking at the moment? So what do you think will be the efficiency from satellite from space to ground? Do you have an idea of what you expect in the future?
Yeah, of course. Thank you so much. So, good morning from Japan. So, yes, now we are expecting the efficiency between transmitting antenna on space to the receiving antenna on ground will be over 50%. And of course, this is a DC to DC efficiency. And beam efficiency between transmitting antenna to receiving antenna will be reached over 90% theoretically if we choose a very huge antenna, very high gain antenna. So theoretically, there is no doubt, so we can reach the 90% of the other beam efficiency, and William Brown has already demonstrated the 54% as a total efficiency from DC to DC via 2.45 gigahertz frequency. So, but unfortunately now we didn't reach such a high efficiency demonstrated by the William Brown, because he adopted the microwave tubes mainly as a transmitter, magnetron. And now we are developing the new semiconductor solid state device. And we would like to control the beam direction for not only for solar power satellite, but also the MIMO WPT system or the SWIFT system. So now I'm expecting to develop the new good solid state, like gallium nitride or the other, to increase the efficiency. So this is my answer.
Okay, thank you very much. And another question that actually was put in the platform is, when you are planning to do this solar power satellite, the cost is going to be huge. So you're going to have a significant cost to actually deploy such an infrastructure. And the comment that I saw on the questions was, how do you see this cost compared with other alternatives for generating power in the ground, even if you have less efficiency from solar panels, for instance? Do you have a comment on this?
Yeah, so thank you for comment. So it's a very frequent question for solar power satellite. Cost is the biggest problem. And of course, now, for example, we Japanese estimate the cost of the solar power satellite will be below $10 billion. But it involves the advance of the very low cost loan system and expect to the expansion of the WPT market to reduce the cost of the WPT system. So now, unfortunately, we cannot realize the solar power satellite with a current loan system and the current WPT system. But in near future, for example, Elon Musk will develop very low cost loan system, and we WPT people will develop the very low cost, for example, solid state or the phased array system. I expect it can be realized. So cost is the most important and the most difficult problem for the future systems, unfortunately.
Okay, thank you very much, Naoki. And this actually take me to the next, well, the next talk will be from Bodan, but is not available today. So if you have a question for the solar power satellite from China, please send it by email or put it on the platform so that we will get sure that you will receive this information. But this takes me to Fritz on WPT Patent Landscape and this cost discussion, I think, fits precisely here, because I saw your presentation. Thank you very much. This is a different aspect of WPT that I think it's very important for all of us. And I saw some of the graphs that the patents on wireless power exploded recently in the last few years. And my question here is mainly focused on, are those patents mainly academic patents? That is, there are professors that are publishing patents, or it's also a commercial patent approach, and you are seeing a lot of activity in the commercial field from these patents? And thank you very much to join us today. So if you want to address these issues. We cannot hear you. I think you are muted. I think there is a problem.
Can you hear me now?
Yes. Yeah, much better. Yes, now we can hear you.
Great. It's
Okay,
nice to have an old landline at the house that works.
That's good.
Well, yeah, just to clarify, I don't work at the patent office anymore. I retired in August of 2000. But you're right, the workload was not very much in the beginning, and it just really took off about 2007, 2008, like the charts in the on the various slides showed. And each area of WPT seemed to exhibit some sort of explosion in filing activity. Now, as far as who was filing, I mean, there were a lot that came from Witricity with their resonant power transfer with the HO2J50/12. There was quite a few from Auckland Uni Services, John Calvert Boys, and also I would see some from Power by Proxy. And then with RF, a lot from Energus, or Energus, I'm not sure how you say that. And then Qualcomm, but I think Witricity bought Qualcomm's IP assets, as far as I understand. So I think a lot of it was from industry and actual products that they were looking to do, and also from the cell phone side. I think there were a lot from LG and Kyocera. I'm not sure if that's the right pronunciation, in the area of shielding, because a lot of the cell phones are now also charged wirelessly. So I think they were taking advantage of some existing shielding structure inside the cell phone and then sort of changing that a little bit to provide some leakage field protection from the wireless charging.
Okay, thanks. And regarding the two fields that we are covering more or less in this short course, which is the more coupled field that is low frequency and the high frequency RF radiative power, where do you think there is more activity at the moment on WPT in terms of patents and
Yeah, I think traditionally the largest filing area was the inductive power transfer area that Grant was talking about. That's been, I think, traditionally what people normally associate with wireless power. However, before I retired, I was working on a lot more applications that were dealing with RF. And that was, I think, with the idea of being able to transmit over a larger distance and then also target the receiver. So like if you come home one day and you have a phone in your pocket and it needs to be charged, well, there was some kind of central charging apparatus that would detect that you had your phone, and when you walked around or put it down, it would then figure out where it was and then beam power to it. So I think just the sheer number of inductive power, so the closer range, has always been there and continued to be there. But I think there was more activity in the RF area, mainly this sort of power beaming. I think that was becoming more prevalent before I retired, if that makes any sense.
Yes, that makes all the sense. Thank you very much. And as I said, I'm going through all the speakers, and then I will go a second round. So now I will move to Paul Wiener. So the talk was very interesting on gallium nitride, and this is really something that is of high interest. So one of the first questions that I will put here, and I think Naoki is also looking to that, is on gallium nitride diodes. And how do you see gallium nitride diodes becoming an important topic for future WPT?
Well, that's interesting. I mean, we have.
We cannot hear. Okay, yeah.
Yeah, there we go. It looks like okay. I muted. So we have focused on transistors. That was the natural place for us to start in power. I think there is opportunity in diodes, certainly with GaN. In those types of applications, again, we've been focusing on power, lower frequency primarily, except when we talk about the high frequency and wireless power. So diodes really haven't been an area we put a lot of research in. Initial kind of testing, sampling shows promise there, but at least for us, it's further out in our roadmap.
Okay, that's good, and thanks for your answer. But the other topic I saw here is how to combine, and if you want to combine these gallium nitride approaches that you are showing up, what are the power densities that you are considering at this moment with gallium nitride devices?
So what do you mean by power densities?
So in terms of size of the gallium nitride transistor, how much power do you think you can actually extract from such a device?
Oh, I see. It's quite a large range, and certainly will depend on, applications, things like I've heard the other speakers talk about with respect to temperature limits and other sorts of regulatory parameters. Right now, it's quite a large range. We see customers using GaN transistors on the powered side, anywhere from 30 watts up to tens to hundreds of kilowatts. Granted, some of those applications, the higher power levels, you're paralleling devices to get to those power levels. From a voltage capability, we're at 650 volts now. I see us getting to 1200 volts within a couple of years. That'll then double the output power again. On the wireless power transmission side, really interesting. You saw in my talk, we're seeing applications up into the kilowatts now. And then I think, as we see people migrate and get more comfortable with the technology, could step that even higher. And with respect to power densities, customers are able to reduce their power supplies by a factor of 3. So they're, 1/3, sometimes even 1/4 the size.
That's good. And I'm looking also at one of the slides that you have in your presentation, where you have your AC to DC supply followed by a DC to RF amplifier by input matching network to your inductive coil. And the question here is, can we do this all these steps can be done in gallium nitride, or do you think we have to combine different technologies at this moment to actually achieve one of these structures?
Yeah, so I think I think the area that's still in question is on the rectifier side. We see some customers using standard diode bridge and others implementing GaN in a more sophisticated solution. It's really at that cost benefit kind of trade-off with respect to size and efficiency versus cost. And then it also depends on power level. What we're seeing is at the lower power levels, there's certainly benefit in bringing GaN into the rectification stage on the receive side. At the much higher power levels, the benefit isn't as clear at the moment. However, I think that equation will change as GaN further matures and the costs come down even further.
Okay, thank you. Thank you very much for your answers. And now I will move to the next speaker, which is Adele on coupled defected ground structures resonators. And one of the questions I have here for actually this talk is, how do you think the coupled defected ground structure resonators will make an impact on the WPT systems? Can you address this point?
For the coupled resonator defect ground structure resonators, the main idea came from using this defected ground structure resonator in coupled resonator filters. And we applied this idea at the past. We could build a 3-dimensional filter, not planar filter. And nowadays, we are applying this idea for transferring power from transmitter to receiver through this coupling, through these coupled resonators. Because of the high quality factor, so the efficiency is high. And also the structures are very simple. You can do the structure using some structures in the ground plane, or you can make your own resonator using some strips of copper or something like this. And you can integrate, of course, some lumped capacitors to improve the quality factor of the resonator and reduce the radiation to be beyond, to be far away from the radiation of the resonator. So you can store more energy within this resonator, so you can achieve high quality, and of course, you can achieve also more efficiency.
Yeah, but how do you how can what is the increase in efficiency that you expect if we use this type of resonators? Do you have a number that you can share with us?
Yes, we could achieve around 95% or something like this. Also, we could achieve around 4 centimeter in the range of megahertz frequency range.
Okay, so
something I have to mention, please.
Yeah.
The main important thing is the matching between the input impedance of the source and the load. This is the most important thing, because the load itself affects also the efficiency. So you have to deal with the whole system as one, you have to deal with all the load integrated with the coupled resonators as a one system. And you have to consider the load in your design.
Exactly, but this brings me exactly to that question, that is, when you are designing RF to DC converters, the load will change with input power, right? So how these resonators will cope with that approach, or how do you see that aspect?
We noted that the small change in the load itself around the operating point, the change will be around 5 to 10% in the efficiency.
Okay. Okay, that's very good. So thank you very much. I will move because we are running, and I want to give a second chance of questions to all. So I will move now to Hamed, and on the topic of dual band rectenna, my question, and one of the questions that is on the platform actually that got more votes is, if we design an antenna and rectifier separate and convert it in a rectenna, is better than design the rectenna combined together? Or how do you see this approach? So if I understood correctly, the question that was put online is, you should design the antenna and the RF to DC converter separate and then connected them together, or should we design them, the rectenna, as a single board and as a single circuit? Do you have a comment on this?
Yes, actually, our best approach is to design actually an active integrated rectenna. So, like, for example, design the antenna taking into consideration the input impedance of the rectifier circuit. That would be to eliminate as much as possible the matching circuit between them. So that would be, I would guess, the best approach and our next step. Right now, what we did is we designed separate. Actually, we designed the antenna, and then we designed the rectifier, and then we used a matching circuit. And this is our first approach, basically.
And do you think if you design the single circuit with both combined, you'll probably get better results, correct? So that I think.
Yes, definitely. If we manage to eliminate losses in the matching circuit and connect the antenna directly with each impedance matched to the rectifier. That, I guess, would be the best approach to eliminate losses and increase the efficiency.
Yes, and another question that I see here is if you use a linear polarization versus a circular polarization, what is your opinion on energy harvesting solutions for these approaches? Do you prefer to use omnidirectional, or do you think the circular polarization probably will lose some power, but in energy harvesting, what is your opinion on these approaches?
The best actually is to there are more and more of circularly polarized solutions coming, and it would be beneficial, of course, to collect more power. The directional antenna is you can get basically enough power probably to turn on the rectifiers. So I guess both approaches are feasible and doable, and we are seeing more and more of the circularly polarized antennas, basically.
Please, I can add something. Of course, the polarization of the antenna, the transmitter and receiver, if the transmitter and receiver are fixed, so we can use linear polarized. If the one of them is moving, so the best solution has to be circular polarization.
Yes, that's clear. Thank you very much for your presentation. So I think we gone around all the speakers that are here today, and now I have two questions at question and answer, and one question I think is very interesting, and this is for all. So, and the question is, what are the implications of the bio effects from powering at a distance and close to living systems? Example, a phone being charged in someone's pocket or near a human or animal. So I think we can address this from 2 points of view. And my question, and this goes to both of the speakers, if we use inductive coupling or capacitive coupling, you can have your phone on top of a matte surface that is actually charging your phone, and it's close to you, 30 centimeters close to you. That versus the solution that some of the companies, and one of the companies that recently show up a marketing campaign from China that actually are using millimeter wave to power up mobile phones that are meters of distance between the transmitter and the receiver. And the question is, do you think this will have an impact of humans, or how do you see this? So this is not specific to any speaker, so who wants to start kicking off this question? I think is very interesting.
Well, on the this is Human. I'll just take this one on the millimeter wave side. So we've done over the many years, almost 20 years of human studies on the millimeter wave side. So the higher the frequency, the lower the skin depth. So what happens is that the power is absorbed through a very thin layer of your skin. And there's been a considerable amount of human studies done at much higher power levels than IEEE, 10x, 20x higher. And there has been no effect. I mean, even long-term effects, anything to do with, effects such as, cancer or that has not been in general looked at, but anything to do with any malignancy, any skin effects, or any other issues. So I think at millimeter wave, it kind of makes sense because the fundamental absorption mechanism is through a skin depth, so it's a thermal effect. But as you go to lower frequencies, yeah, it changes. And I did look through all the effects for a variety of different And we do have, some of the things that you could look at is like radars, people who operate radars, and what they do. And over the years, you can collect some data. It's not a good idea for lower frequency, but as you go towards the higher frequency, it's definitely becomes safer. And some of the 5G community are actually looking at that much more seriously, and studies are being funded and to look into that. So it'll be good for the WPT community to kind of couple, sorry for the use of the couple, but couple into that and leverage that. And that's what we should do. We should kind of take that seriously on that, but I'll let others speak.
Okay, that's very good. Yes, Glenn, please.
Oh, I was just going to add that from the low frequency side, there were a large number of studies done that showed that actually a lot of the IC and IP regulations are very conservative, so there's very little impact in the kilohertz range on the bodies. But when we come to standardize it, we of course are looking more generally at what IC and IP recommends, and we're particularly sensitive always to these fields as an interferer. So it's not just to do with body and SARS effects. It's also to do with are there pacemakers that people are wearing that could be, or other devices which could have been designed and their legacy out there which could be interfered with. So generally, when we come to standardize, we look at a range of things and look at the application case and say, how do we ensure that this product is safe when it goes into its intended usage? Now, of course, when we look at wireless power in kind of the contexts which I do for industry and for EV charging and stuff, the power levels are going up quite high. So you want to constrain that field to where humans aren't and ensure the leakages aren't going to interfere with all of those devices. As you move down to lower powers, the use case is different, but we've always got to consider, where could these fields end up if they're just everywhere? So, and what might they interfere with? So I'd be really interested to get Paul's view as well, who's working at the higher frequencies, probably not these frequencies, but get his input on some of this as well.
Sure, yeah. So I think what we tend to see, so we're typically building systems at 6.78 and 13.56 megahertz. And what we typically see is that, for the systems we build, a few hundred watts up to low kilowatts, it's actually, it's relatively straightforward to be within the ICNRP regulations at those power levels, even at those frequencies. The difficulty, as Grant was suggesting there, is other bits of equipment that you might interfere with, particularly medical equipment. So actually the thing that is probably the biggest pain point for us from a design perspective, particularly with the open core systems that we build. So one of the things we say with the megahertz stuff, and you'll have seen this in the talk, is that we're trying to create systems that have a very high degree of freedom of movement between transmitter and receiver. And if you're going to try and do that, then fundamentally you can't constrain the flux, because if you constrain the flux, you're relying on the receiver being in a well-known location. So as soon as you move into these systems, high frequency to get high Q, to operate with low K, to get a big distance between transmitter and receiver, to get big misalignment capabilities, you're opening yourself up to uncontrolled, well, not totally uncontrolled, but a much broader volume, energized volume over which the flux is active. And then you have got to be careful, particularly with pacemakers. So as I say, certainly up to the hundreds of watt systems that we build, ICNRP is not a problem, but the pacemaker aspect becomes more of a problem. And then you're looking into, and something we haven't really talked about very much yet, foreign and live object detection systems, which is probably a whole panel session worth on itself to go into the details of that.
I have an additional comment. I fully agree with the consideration of my colleagues, but we have to be careful about the public concern. I remind what's happening with the introduction of cellular phones or now with 5G technology. And so I think that also for WPT will be a lot of problems with public concern. This is my personal opinion. So we have to be very careful about that and to study a lot these aspects.
Yes, for sure. I think Naoki wants to say something also. Yeah.
We have to divide this point into the bioeffect and EMC problem. So as a bioeffect problem, of course, as you know, we have a regulation of the safety in the world. So we have to keep this safety level. And of course, but we, WPT guy, would like to transmit a higher power to the receiver. So in this case, we cannot keep the safety level into the transmitter and receiver. So in this case, we have to use a time and space only. So time means we have to stop the wireless power when we detect something between the transmitter. And space, this is, I suppose this is only a technology for far field. We have to control the beam direction and we have to avoid the human or the animals by beamforming technology. For example, OCR's company Quota is one of the most famous technology to avoid something by the hyper beam. So this is my opinion. And about the EMC problem, I have one information for all. So in parallel, we have the ITU discussion in this week and last week. And so 8 hours ago, we have some agreement about the EB WPT and far field WPT. But it's very, very, very hard negotiation. And we need your support from individual researcher and government support. So unfortunately now, WPT, a lot of countries, for example, China, UK, or the other countries are unfortunately negative, I feel, for the WPT, and US, Brazil, and Italy, Japan push the WPT to the ITU to harmonize the wireless communication group. So we need your help and support. And if you can attend the ITU, or if you know the delegate of the ITU in your countries, so please ask them to attend the ITU, and if possible, please attend the ITU by yourself. Thank you so much.
Okay, thank you so much. And Naoki, since you are the last to talk, there is another question here that I think is you can actually answer also. And someone is asking if a big rock contains a lot of metal in space, comes between the transmitter and the receiver of a huge wireless powered link, what could be the potential hazard of that? And do we have a method to detect this kind of hazard in space WPT?
Yeah, I think so. We have some technology of the beamforming and target detecting by the radio waves. So it is named the retrodirective system. So I think it's easy to detect something between the transmitter and the receiver, not in space and on the ground. So if we have a good technology of the beamforming and target detecting like retrodirective, I think it's easy to develop it. And so we Kyoto University have developed some safety beaming WPT system by suddenly stopping system and detection of the beam, detection of the unexpected beam. So for in the far field system, I think we can do it.
Okay, thank you very much. Well, the other question I have to all the panel is, and if we start combining techniques, so I'm assuming that combining inductive coupling with capacitive coupling would be something that is easy to do. The frequencies are similar, but also combining RF WPT with low frequency WPT can be of use in certain use cases, certain specific use cases. But I will kick off this with Karam and probably Grant, Paul, and Dulipa. So if we combine inductive coupling with capacitive coupling, do you think it will be worthy, or you don't think it makes any sense?
I can take a stab at it. Actually, the person who's actually done some work on it is Chris Mee, who's is the chair of our conference. We should really ask him. But from what I remember of his work is that the geometries and the just sort of the spatial dimensions and the frequencies involved in at least the system he designed just didn't work out to a benefit, overall benefit. However, if the inductive system and the capacitive system could be sort of engineered in some clever way, I'm sure somebody could come up with a mechanism to gain benefit. But I haven't worked on it myself, so that's pretty much all I'm going to say.
Yeah, we have a colleague of ours, Professor Patrick who did a little bit of work on this, and it's many of these things are use case, because you're looking at saying, well, what could we use this here for? So in his case, he wanted to do some capacitive coupling because there was some metal shields there, and then he inductively coupled from the back end of that to something else. So you could use it beneficially to when you've got something which would naturally block an inductive field, you can couple power capacitively and then maybe go inductive to the next stage. I've also seen both capacitive and inductive used in foreign object detections for various mechanisms for working out. But as Kuram said, sometimes what you're looking for when you're designing a system is you're looking to get the complexity down. So, you know, there's got to be really a good use case for making something. It's a little bit like saying we're going to try and bring together a hybrid vehicle. So you're going to have two systems in there, and then you've got the complexity of two systems, which can bring benefit in some cases, but in other cases, you know, maybe if you could refine the design of one system, you would get what you want. So I think it's a case by case, but I think generally what you're finding is the use cases vary depending upon, you know, what your target is, and you can design your system more efficiently, keeping it as simple as possible. And certainly when you're dealing, you know, with industries that I deal with, they're always driving the cost down. It's never bring me extra complexity, but if there's a good case for it, they will. For example, if it saves them money, yeah, they'll grab at it.
Sorry, I was just going to add a little bit. I thought it was kind of interesting how Nuno, I think, used the phrase, it must be straightforward to integrate these two solutions. And I think that's one thing, that's a word I've stopped using in engineering. But I just sort of anecdotally, one of the things that I think we've seen, although we haven't completely bottomed it out, is that particularly with our systems, when we move up to 13 megahertz, we do get some capacitive coupling between the transmit and receive coil, even though we've designed it to be an inductive system. And actually that's a real problem, because it can, as you then change the proximity of the transmit coil and receive coil, even that small bit of capacitive coupling can significantly detune the inverter. So it's a straightforward problem, perhaps.
Yeah.
Can I jump in real quick and add something? Oh, sorry, Fritz Fleming here.
Yes.
I mean, if you just wanted to see if people have done this before in the patent literature, you could go do a search in CPC. You could H02J50/05, which is using capacitive coupling with /10 or 12, which is your inductive coupling. And you could just look at the results of a simple ANDing operation without using any text search. And that should pull up patent documents that have both types for power transfer. Because it is pretty common to see in an inductive power transfer system, capacitors in there that are used for data transfer, not for power. But the beauty of the new CPC classification scheme is that you can look at various technologies and just sort of play around with them and them together and see what turns up without getting too bogged down with text terms. So if anybody's interested in trying to look, you can use any one of those internet search engines like SPOSnet from the EPO or the Lens. And they're all set up where you can just and those things together and get your answers really quickly.
Okay, that's good.
Quickly to add to Karam and Grant is I've seen the work Chris has done around that, and also Patrick's done a bit of work around that. And there's also some other publications coming from Stanford that it's not purely for capacitive power transfer, but they're using the capacitance of the coils instead of using separate capacitors to resonate. That has some benefits in their use case. So that's another avenue people are looking at, not inductive and capacitive power transfer, but using the capacitance of the coils as means of creating the resonance rather than using external capacitors.
Yeah, for sure. Yeah. Thank you very much all to actually comment on this. I have another question here, which I think is very interesting, which someone is asking, could you please talk about application and feature trend of multi-relay WPT systems or domino WPT systems? And this is also, I think, not only for low frequency coupled solutions, but also in RF, there are some approaches where you can have a device that operates like a receiver or a transmitter of energy, and they can be switched from one side to the other, so they can actually relay your energy. Do you have any comment on this and how we are going in this direction?
Yeah, I'll start off, but I'm sure others can add. So Ron Huey's done quite a lot of work in this area, but is not the only one. So in his case, the use case was because you could put in a robotic arm, for example, and you could bend the arm around and you could then relay the power around. As you're creating the domino effect, of course, what you do have the individual losses of those resonating coils to deal with, but you get an effective power transfer is much better than trying to transfer it over the range. So you can also constrain. So we've used intermediate resonators to transfer power, significant amounts of power while constraining the leakages, which you can't do if you're trying to get over a large gap and you've got to push a certain amount of volt amps to get the power transferred across. With constraining leakages or shaping it, and that's we're not going into the high frequency area where we're beaming, but we're in the coupled region. So domino effect is quite good for that kind of application, and also for trying to push the field in different directions. So that's really quite possible to do that, and I'll be interested in other people's views of other work they've seen.
There's a spin out from University of Oxford in the UK called Metaboards, which is looking at a similar sort of thing, where they've got a chain of resonators that sit on a table, and the objective is to be able to put a piece of equipment anywhere on the table and it gets powered. And they've got this set of effectively like domino resonators as a surface underneath the table, transferring power from one to the next. And then there's some routing as well in order to get power from the edge of the table or from the middle of the table out to wherever you put the piece of equipment. The problem, of course, with that solution, and Grant also just alluded to this, is that it can be quite lossy. You've got to go over multiple hops, or you've got multiple resonators in the chain, and losses associated with each one. So I think the metaboard solution from memory, their typical efficiencies are certainly below 50%.
Yeah, one other application that you can use it for, and I've seen this used in other cases, but I think Chris showed this, is you can have a domino effect where you're wanting to, for example, applications like driver boards, and you're trying to drive switches on some sort of palletronics, and you can bounce the field across and extract the field out for various secondaries that they're using, and so you're not having to make the physical coupling. So you've got one primary, and then you're bouncing the field through a string. So that there are use cases, I think, for this nano, which have some benefits.
While I was at the patent office, I would see some of these, and the term that they used was repeaters. And the older area in CPC was, let me look here, H02J50/50, which is using energy repeaters. And then what I think was just mentioned, where you have some that can switch between being a receiver and transmitter. That might be in the newer area of 50/502, where they integrate the repeater in with the receiver. So in effect, you could have, say, a receiver that takes in some WPT and then puts it back out the other side in order to sort of increase range. And I think most of these I had seen with in the IPT area, especially I think the resonance coupling.
Yeah, so one of those we did that Fritz, you're probably talking to, with, so there's one that we did with John and I did with for lighting. So we had a track system, and we wanted to get lights up a meter from the track for roadway lighting, or for lighting a lamp. And so we just coupled resonance from a resonant track, and we had a repeater that basically through a tube bounced it up to get to the light on the top, a meter up, where some were right next to the track, some could be bounced up. And so the use cases for this can be quite efficient if you use it in the right applications, I think.
Yeah, on the radiative side is also extremely attractive, because you're going now to non-line of sight power transfer by using the repeaters, which actually that's what I'm used to, the word, as Fritz mentioned. And integrating the transmitter and receiver together also has its own attractions, and especially because you can change frequencies if you wish to do so. And as now also mentioned, solid state technology allows you to be very, very compact and have these various panels that could do a variety of different work for you. However, that's kind of really sophisticated way of transferring power, where I know we're, as kind of technologists, we're always very, very cognizant of efficiency, but at some point efficiency is a metric, but is not the most important metric. Is delivering power. Let's say, for example, if you mix power and signal together, efficiency doesn't, because it is an important one, but if you do have sensitive receivers on the other side, or whatever you do, you could start to think about functionality being more important than overall efficiency, in which case repeaters make a big difference. But yeah, I mean, there are companies out there already in the radiative side. I think Emrod is one of them that we've seen that they are touting the kind of the repeater technologies that goes forward for the radiative side. But yeah, I think the prospects of that is rife with a lot of good technology to come.
Okay. Yes.
Yeah, so 8 years ago, Professor Yagi and Uda did the repeater technology in the far field. They named it web canal. So I think we can do it what wireless communication did. So it's the same radiation, radio wave technology. So sweep, repeater, domino, or the other, we can do it. All of the what wireless communication did, I think.
Okay, so I think we got to our time. So it's now 2 a.m. in my country. I believe it's 3 a.m. in Italy, and it's morning and afternoon in the other sides of the world. And I would like to thank you all for being here today. I think it was an amazing discussion and session. I will share, if you don't mind, very fast, I will share the webpage for our WPT IEEE initiative. So feel free to come to our website and actually have a look of other activities on WPT around the world and some of the issues that we are bringing out. So this school is the third year that is being organized, and it's going to be organized again next year in the new WPW conference that is going to be in Bordeaux. So you are all welcome to come to our new WPT school next year again. And I think it was very well attended, and I'm very happy with this group of people that actually stay here 1.5 hours listening to all these very great colleagues talking about WPT. And now I give the word to Chris Mee, our general chair today. And from my side, thank you very much.
Thank you, Nuno. Thank you. This is such a great discussion. I like it. I love it. Thank you all. Thank you all for your contribution. And we're going to look forward to seeing all of you tomorrow at the opening, which is at 9 a.m. My time. Thank you, and have a good night or good day, depending wherever you are.
Thank you.
Bye.
Thank
Bye
you.
bye.
Bye-bye.
Thank you all.
Bye.
Bye bye.
Thank you very much. Thank you all.
Bye now.
Bye-bye.